Recording. So is the screen visible? Just can anyone just confirm, because I have just joined again. Can you hear me first of all? Yes. Okay. Okay. So let's start the session. Just a minute. Yes. Okay. It's time. So the first question is whether or not this function. So again, those who did not attend the last lecture, my general policy is the questions which are correct. The questions which are correct, I am answering them by the blue statement. Question mean the options. So the first question is which of the following are true, and it is an MSQ question. So it can have a multiple options as correct or as incorrect. So in the question one first part, it has been asked that this function ez square, is it an entire function? So we know that a composition of entire function is an entire function again, right? So you take f1z to be z square and f2z to be ez, and both of these are entire functions, right? They are from c to c. Then you see that f of if I compose f1 with f2, so it will be f1 of z square, but f oh sorry, f2 with f1 I should, f2 of f1, yes. So then f2 of z square, it will be e of z square. So in this way it is an entire function, because each f1 and f2, each of them is an entire function. So therefore their composition is also an entire function. Okay. Then the second question is, if f is an entire function and g is not an entire function, g is not an entire function, then f plus g is not an entire function. So think of it like this: if f is an entire function and g is an entire function, we know that the sum is an entire function. So this question asks, what if one of them is not an entire function? Okay. So the answer is no, it won't be an entire function. Why? Why? Sorry. Mm, Because let's say if f plus g is an entire function, okay, if f plus g is an entire function, okay, then g can if then g can be written as f plus g, or yeah, f plus g minus f. Now if f plus g, if you assume that this is an entire function and f is already an entire function, so the difference of two entire function is again an entire function. So this will be an entire function, right? So then g will be an entire function. But this is a contradiction. Why? Because g is given to be a non-entire function. So this way, this is correct, that the sum, if one of them is not an entire function and another is entire function, then the sum is not an entire function. Okay. Now the third is, there exists two entire function. There exist two functions. You don't know whether they are entire or not. Okay. So it says that there exist two functions which are not entire, which are not entire, but their sum is entire. Okay. So this question basically means that the sum of two not entire functions, it can be an entire function again. How can you say that? See, any entire function, if you take fz to be real part of z, okay, gz to be imaginary part of z, iota times imaginary part of z. Now when you add these two function, you will get real part of z plus imaginary part of z, but this is nothing but z. So f plus g will be z. It will be an identity function, which is an entire function, but the real part and imaginary, this iota times imaginary part, they are not entire function. I think someone is joining. Let me just check. Yes. Student, please come on time. I request you, all of you, to be on time. Yes. So f and g are two functions which are not entire. Why the real part of z is not entire? Because it won't follow Cauchy-Riemann equation. Or if you have learned the fact that every real valued function cannot be holomorphic, therefore in that particular way you can also say that f is not going to be an entire function. Similarly, g is not going to be an entire function. The easy way to check that these functions are not entire is to go via Cauchy-Riemann equation. Okay. Now fourth question. So fourth question says, if f is an entire function and p is a polynomial in one variable, then their composition is an entire function. We know that a polynomial function is an entire function because a polynomial function is differentiable. Okay, at any given point it is a differentiable function, so hence it is an entire function, and composition of two entire function is again an entire function. Okay, so this option is correct, that so this p composed with f of z, what is this? This is nothing but composition of two entire function. Okay. Now the fifth question says that exponential is a surjective map. Okay, this is not true because exponential can never be zero. So exponential can never be zero, and this we will prove. See, okay, so this is the proof, but I will write. You can write 1 as e power 0, right? And then you can write, okay, so if there is z naught in C, if there is z naught in C such that e power z naught is 0, okay, let there be z naught in C such that the e power z naught is 0. Now you can write 1 as e power 0, right? But e power 0 can be written as z naught minus z naught, and exponential is multiplicative in the sense that it splits, right? So this e power z naught minus z naught will be e power z naught times e power minus z naught. But what is e power z naught? It is 0. 0 times e minus z naught, it has to be 0. So this way, this is a contradiction. Okay. So this is not possible. Exponential can never be a zero value. Okay. Hence, because it is skipping 0, in the range of exponential, there is no point which will map to 0. Hence, the exponential function is not surjective. It is not surjective. Okay. So is there any doubt up until now? Please ask if there are any doubts, because then we'll move to the next question. If there is none, then I'm moving to next question. Okay, has someone put something in the chat box? Okay. No, sir, no doubt. Okay. So, have you guys learned isometry in your class? Okay, so isometry is a function which preserves distance. Okay. So it is a distance preserving function in the sense, in the following sense: a function f from c to c is called an isometry, if mod of fw minus fz is same as mod of w minus z. Now, how this is a distance preserving function? See, what is mod w minus z? It is distance between z and w, right? It is distance between z and w. And what is this fz minus fw? It is distance between fz and fw, right? Now isometry says if a function is isometry, it says you take any 2 points in the domain. Okay, let me just write. So yeah, so isometry. Just so yes. So what does isometry is? What is an isometry? It is on complex plane. Okay, we are talking on complex plane. A function f from c to c such that fz minus fw. This is the distance, right, between fz and fw is same as z minus w. So here is this complex plane and here is this range. Now f maps this complex plane, I mean, into this complex plane on the right hand side. Now isometry means basically if you have 2 points z and w, let's say z and w. So here you will have some distance, right? So this is mod z minus mod w. This is the distance. Now let's say under 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 using the map f, it goes to somewhere. Let's say this is f of z. Okay, and w also goes to some f of w. Now the isometry says that this distance will be same as, so this distance is fz minus fw, right? So isometry says that these two distances will be same. Okay, so this is the precise meaning of isometry. Iso means same, metry means distance. So in some sense it is a map which preserves distances. Okay, so some examples are, if you translate this fz equal to z plus z naught, this is one example of an isometry. You can check by definition. Okay, or if you are rotating, so okay, let me write. So if you define f of z to be z plus z naught, now this is an isometry. Why? Because if you consider fz minus fw, it will be z plus z naught. Z naught is fixed. Z naught is fixed. It can be 1, 2, 3 iota anything. Minus w plus w naught. Now if you saw, sorry, w plus z naught. W plus z naught. So it will be z minus w, right? Z naught and z naught will be cancelled. Another example of isometry. So this is called translation, because you are translating. When you add a vector, you are translating, right? Another example is rotation, e iota theta z. You again do this. So it will be e iota theta is fixed. Again, theta is fixed. E iota theta z minus e iota theta w. You can take e iota theta common, right? And here you will have z minus w. So you can write it as mod of e iota theta times mod of z minus w, right? And mod of e iota theta is 1, because mod of a 30, this 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 is 1, so hence these two are same. So these are some typical examples of isometry. Yes. Okay. So now what we do, just a minute, yes. Now we classify. Before moving to the next question, we study a lemma. Okay. And another example, another useful example of isometry is the following. It is the conjugation map. Fz is z bar. Why? Because Fz minus Fw, it is z bar minus w bar. It can be written as z minus w whole bar, and we know the modulus of a complex number is same as its conjugate, so it is again z minus w. So this map is called conjugation. Conjugation. So these three examples are really important, which will be used in the exercises of this assignment. So finally we move to the classification of isometries in the complex plane. So first lemma says that if H is an isometry such that it fixes 2 points. So it is fixing 2 points, 0, 0, 0 and 1, right? Then this lemma says the only possibility is the identity map or the conjugate map, which means identity map and the conjugate map are the only isometry which fixes 0 and 1. Okay, so this we will prove. Now, using the fact that H is an isometry, we know that mod of Hz equal to mod Z. Why? Because see, mod of Hz minus Hw, it has to be mod Z minus mod W. So if you take W to be 0, then you will have Hz minus H0 will be mod Z minus 0. But H0 is 0, right? So finally you will have mod of Hz equal to mod Z, which is this equation. Okay. Now if you put, again you put W equal to 1, that is Hz minus H of 1, it should be equal to mod Z minus 1, but H of 1 is 1. So you will get this equation. Okay. So using 2, let's say this is 1 and this is 2. So if you square 2, if you square the equation number 2, you will get mod of Hz minus 1 square equal to mod of Z minus 1 square. But we know that for any complex number, mod Z square equal to ZZ bar, right? So we have used this thing here. So it can be written as Hz minus 1, Hz minus 1 bar, Z minus 1, Z minus 1 bar. Now you open the bracket, which we call the distributive property, and you will get the following. Okay, let me do the calculation because otherwise. So from here you will get LHS, you will get Hz minus 1, Hz minus 1 bar. So bar will split. Okay, and it will be equal to Hz minus Hz bar minus Hz minus Hz bar plus 1. Okay, so which is the same as this written over here. And similarly for the right hand side you will get this. Now again we can convert it into the mod. Okay, so we know because H is an isometry, so using equation 1, so 1 implies that this will be same as this, right? So they will cancel out, and this 1 will also get cancelled out from here. So what you get is Hz plus Hz bar is Z plus Z bar from this. If you divide it by 2, you will get real part of H of Z is same as real part of Z. So hence you have, so finally from all of this, So from all of this, so what we have proven so far, that real part of hz is real part of hz is real part of z. Okay, so hz is actually hz. How can you write hz as? It is, by definition, it is real part plus its image iota times imaginary part. Now this is real part of z and plus imaginary part of h of z. So this we have proved. Now use again mod of hz is actually equal to mod of z. So what is mod of hz? So their square will also be equal, right? Their square will also be equal. So on, on LHS, so this will be equal to mod of real part of z square plus imaginary part of h of z square. By the definition, if z is equal to x plus iota y, where x is the real part, z is the imaginary part, mod of z square is x square plus y square. Okay, and this will be on RHS, you will have real part of z square plus imaginary part of z square. Now these two will cancel out. So you will have mod of imaginary part of h of z is same as mod of imaginary part of z. Now remember, all these are all these are real number. So if mod a equal to mod b, where a and b are real number, now what is the possibility that a equal to plus minus b? This is the only possibility, right? So this implies that imaginary part of h of z is actually plus minus imaginary part of z. Okay. So in case one, h of z will be real part of z plus iota times imaginary part of z, in which case it is nothing but z. And in case 2, it is real part of z minus imaginary part of z, which is nothing but z bar. Okay, so we have proved the only two possibilities. Is this clear to everyone? If not, then ask. Is this clear? Okay, I am assuming that because you are not asking, so this is clear. Okay. Okay, so I'm deleting all of this. Now what if, why did I write that? Yes. So now one lemma we have, that if phi be an isometry of C which fixes the origin. See, in the previous case, that H was an isometry of C, the complex plane, which was fixing 2 points, origin as well as the point 1, z equal to 1. But in this lemma, we are characterizing all those isometry which fixes the origin. Okay. So in that case, it is phi z, either it is alpha z or alpha z bar. See the similarity. Earlier it was hz is z or hz is z bar, but here a multiple is coming, a scalar multiple is coming, and that scalar multiple is from the unit circle. So how do you prove it? You assume phi of 1 to be alpha, take phi of 1 to be alpha, and define, and because phi is an isometry, so phi of 1 will be mod alpha, which should not be 0, right? Because if mod alpha is 0, it will imply alpha is 0, which implies phi of 1 is 0, but phi fixes origin, so it is 0, but phi is an isometry, so it is 1 1, so 1 equal to 0, and this is a contradiction. So alpha is not 0, hence we can divide phi by alpha. So consider this new function hz, which is phi z by alpha. So again, this is an isometry which fixes 0 as well as 1. So hz has to be either z or z bar. But what was hz was, and why is it an isometry? See, because phi of 1 we have chosen it to be alpha, so mod of phi 1 it has to be mod 1, which implies mod of, which is 1, so mod of alpha has to be 1. So if hz is z, this implies phi z is alpha z, or if hz is z bar, it implies phi of z is alpha z bar. Okay. So we have characterized all the isometries on the complex plane which fixes the origin. Okay. And why we have done all of this? Because we want to deal with the next question. Okay. So the next question says, if I denotes the set of isometries of C which fix the origin, we know there are only two up to the scalar constant. It is either alpha z or alpha times z bar, right? Where alpha belongs to the unit circle. Now, which of the following statements are true? Which of the following statements are true? So, first statement is again the statement whose answer is correct. I have given the solution in the blue color, and the statement whose solution is false, I have given the solution in red color. So, suppose that z is not equal to w or two complex number, non-zero complex number. Then the only isometry in I which fixes z and w is the identity map. This is false. Why? Because choose z equal to 1 and w equal to 2. Okay. Now these are two non-zero, not equal complex number, right? They are real numbers, so they are complex number also. Now consider the conjugate map. So conjugate map is an isometry in I. Why? Because in I is what? I is either alpha z. I mean, these are two maps. Either z goes to alpha z or z goes to alpha z bar, where alpha belongs to C such that mod alpha is 1. So z is of the second form. Alpha is 1 here for the conjugation. Okay. So this is an isometry in I which fixes both 1 and 2, but it is not an identity map. Okay. Why? Identity map means z goes to z. But in this case, iota will go to minus iota. So this is not true. Hence, this statement is given in red color. Now, again there is some question which says, if there are two non-zero complex number, then there exists an isometry in I, non-trivial isometry. Non-trivial means which is not the identity. Non-trivial means which is not the identity. So it says if you take any two not equal complex number, then there will be a non-trivial isometry in I which fixes both z and w. So the answer is again false. See, the first thing is, you see that we have only two possibility to check: phi z equal to alpha z or phi z equal to alpha z bar. Okay. So take z equal to iota and w equal to 1. Any isometry in I, because we want an isometry in I, right? We want an isometry in I. It is given. So it is either z goes to alpha z. Okay, let me use blue color. Or it is z goes to alpha z bar for some alpha mod equal to 1. Now let's consider case 1. So this is my case 1. So if phi of z is alpha z, which means you put iota, it fixes iota also. So you will have iota equal to phi of iota, because it is fixing iota. We have assumed that it fixes iota and 1. Okay. But by definition, phi of iota is actually alpha iota. So this implies iota equal to alpha iota, iota equal to alpha iota. So iota will cancel out and it will imply alpha equal to 1. Okay. Just hold on, guys. हेलो। अरे मैं क्लास ले रहा हूँ, बाद में करता हूँ। हेलो। Yes. So alpha is 1. Now if you put alpha is 1, then it will become an identity map, right? So, but we do not want an identity map. Okay? We do not want the identity map because we are in the search for a non-trivial isometry. Okay? So we are left with only one case, which is phi z equal to alpha z bar. Okay? So if phi z equal to alpha z bar, then at z equal to iota you put, because it should fix iota. So phi of iota, because it is being fixed by, because iota at iota, phi is fixing this iota, so iota should be equal to phi of iota, but by definition it should be alpha times conjugate of iota, which is minus iota. So this gives alpha to be minus 1, right? But if you take at 1, because it phi is also fixing 1, so it will be 1 equal to phi of 1, but phi of 1 by definition it is alpha. So it is alpha equal to 1. So alpha is getting two different values, which is not possible. Okay? Because it will imply 1 equal to minus 1, which is a contradiction. Okay? So this option is also false. Now the next question is, yes. So next question is, if z and w are two non-zero complex number such that w equal to rz, so which means w is a scalar multiple of z. Now what does it mean? If this is z and w is some, if this is your z, and if w is a scalar multiple of z, so which means it lies on this line, right? They are collinear points depending on r. So w will be somewhere on this line. Let's assume it is here. Now the question is, does there exist a non-trivial isometry which fixes both z and w? The answer is yes. So let this line be L. So you just reflect. So reflection along the line L, we know that this is an isometry. Reflection along the line is an isometry. Okay. So the reflection, what does reflection mean? That you reflect this side to this side. Okay. So this such a map forms an isometry, and every point on this line L gets fixed. So hence in particular z and w, because they lie on this line, will also get fixed. So this option is true. Okay. So you just see that this option is also true. Now fourth option is, if so fourth option is about characterizing all the isometry of C. So we have characterized every isometry of C which fixes the origin, right? Now what about the isometry of C which need not fix the origin? So let phi be an isometry of the complex plane, not necessarily fixing the origin. Then it should be, then there is a typo. Then phi of z, either it is alpha z plus z naught, or it is alpha z bar plus z naught for some fixed z naught in C and mod alpha equal to 1. Now how do we prove it? This option is true. You start with an isometry phi, you define a new map phi z minus phi 0. Now because phi is an isometry, so this phi z minus phi 0 will again be an isometry. Why? What do we have to show for isometry? That phi z minus xi z minus xi w, it has to be equal to mod z minus mod w. Now phi z minus phi 0, again minus of phi w, minus minus plus phi 0. So it is nothing but phi z minus phi w, right? But phi is an isometry, so it will be z minus w. So this map xi, it will be an isometry, which fixes the origin. Why? It fixes origin, right? Phi of 0 minus phi of 0, it will be 0. So by that lemma that we have done earlier, it should be either alpha z or alpha z bar for some alpha with modulus 1. Now you again put the value back. So you'll get phi of z equal to phi 0 plus alpha z, or phi z equal to phi 0 plus alpha z bar. Now choose your z naught to be phi 0. Is it clear? Okay. Now the fifth question is, it says if you start within any isometry of C, then phi does not have a fixed point. So now what does it say? It says any isometry of C except for the region, or except the one fixing the origin, it won't have any fixed point. This option is false. Why? See, this is an isometry, right? Because it is of the form alpha z plus z naught, where alpha is 1. So which implies mod alpha is 1. So by question 4, we have done in question 4 that any map of this form is an isometry. Okay? So phi z equal to minus z plus 1, this is an isometry. And if you compute phi of half, it is minus half plus 1, which is half. So it fixes half. So it has a fixed point. So fifth is false. Okay? Isometry can have a fixed point. Now the last option, if you have an isometry of this form, z plus z naught, where z naught is not 0, then it does not have a fixed point. It is true, right? Because if phi z is z for some z, then it will imply they will cancel out. It will imply z not equal to 0. But this is a contradiction. Why? Because z naught is assumed to be non-zero. Okay. So the statement that phi does not have a fixed point is true, because otherwise z naught will become 0. So up until question 2, if someone has any doubt, please, because these were the long questions. Now everything is easy. Okay. Now this argument, by the definition, this argument is the principal argument which is taken in this interval open minus pi to close pi. Now the question is, compute this value. Okay. So what is minus 1 upon root 3 plus I? You just rationalize it. Okay. You just rationalize it, and you will have just a minute. So you will have minus root 3 plus iota. What I want to say is the following. Okay, okay. Yes. So you know that if z is r iota theta, then 1 by z, and z is not equal to 0. Then 1 by z is 1 by r e minus iota theta. So this gives argument of z is actually, so this theta becomes minus theta when we are going from z to 1 by z. So argument of z is same as minus of argument of 1 by z. We have used this. Okay. So if you take z to be 1 upon, if you take z to be, you choose your z to be this. Okay. So it will be minus argument of reciprocal of this, which will be minus root 3 minus iota. Okay. Is this fine? So why this statement holds true? Because argument of z is same as minus of argument of 1 by z, where z is not 0. So all it boils down to computing its argument, and you can see that this argument is minus 5 pi by 6. Okay, this is just class 12th algebra. So you just put this value, and you will get answer equal to 5. See why, so we have to compute this argument, right? So we have to compute the argument of minus root 3 minus iota. So your minus root 3 somewhere will be here and minus iota will be here. Now the argument is it belongs to minus pi to pi, right? So half of the angle you measure in this direction and half of the angle you measure in this direction. Okay. So this angle you can find using the trigonometry. If this is theta, then tan theta will be equal to, so this length is how much? 1, and this length is root 3. So tan theta will be 1 by root 3, which will give you theta equal to pi by 3, pi by 6, 30 degree, right? So this angle, okay, let me just redraw it again. If this is your minus root 3 minus iota, so this angle is pi by 6. I mean this angle measured from this. Now, so but for the principal argument below the below the first half, you measure angle from here. So this angle will be 5 pi minus pi by 6, which will be 5 pi by 6, right? Because total this length, this angle is pi, this semicircle is pi, and already this is pi by 6, so answer will be pi minus pi by 6, which is 5 pi by 6. But you are because you are measuring angle in the anti-clockwise direction, so minus has to come, so the final answer will be minus 5 pi by 6. Okay, which is precisely done here. So this is precisely what we have done. Now you just put the value. Okay, so answer will be 5. Okay, so question fourth, again it is some argument calculation. So we one can see if this is your complex plane. So 1 plus iota, 1 plus, which means 1 and iota, right? So it is 1 plus iota. So this angle clearly is pi by 4. X equal to y always form an angle pi by 4. So 1 plus iota in the polar coordinate can be written as root 2 e power iota pi by 4. So hence 1 plus iota 7, it has to be root 2 power 7 e7 I pi by 4. But 7, so 7 I pi by 4, it does not belong to minus pi to pi, right? We want, we have been asked about the principal argument which belongs to minus pi to pi. So you just subtract 2 pi from this, sorry, not iota, 7 pi, and you will get minus pi by 4. So angle is same when you subtract or add 2 pi, angle does not change. Okay, but this now belongs to minus pi to pi. So hence in the polar coordinate form with the proper principal argument, your iota 1 plus 7 is actually root 2 power 7 exponential power e minus iota pi by 4. So the principal argument of 1 plus iota 7 is minus pi by 4. Okay, just a minute. Yeah. So the answer is, so if you put minus pi by 4 here, your answer will be minus 1, right? Because pi they will cancel out and 4 will cancel out, only minus will remain. So the final answer is minus 1. Now fifth question is you must have seen many times, but okay, let's discuss. So we have to prove which of the following inequalities are true. Sine square z plus cos square z equal to 1. We know in the real case it is true, and but in the complex plane, how do you define cos z? It is using this identity, right? So this, you use this identity and your conclusion follow from direct computation. Okay, I'm not going to prove this. Just use these two identities. Now for the second, is mod of sin z less than equal to 1 for all z equal to for all z in C. In the real case, it is true, right? We know that mod of sin x is less than equal to 1 for all x in real, but it does not hold true in the complex plane. An example is you take sine 10 iota, you take z equal to 10 iota. Okay, you take z equal to, you choose your z to be 10 iota, and by this formula, what is sine 10 iota? It is e iota z. So z is 10 iota minus e minus iota 10 iota by 2. So when you do the calculation, you will get mod of sine 10 iota, it is equal to this, e 10 minus e, sorry, yeah, it's same, e minus 10 minus e power 10 by mod. And you can use anything, or you can use a calculator or any general calculus, or simple algebra you can do, and you can prove that this is actually greater than 1. So hence you have one counter example in your hand. So this statement is false. Why is there a repetition? Oh, sorry, like yeah, this should not be a part. Yeah, I have already done this. See, again, to prove the third identity, you just use these two definition, sine and cosine. And the next two identities are about the sine hyperbolic z and cos hyperbolic z. Now how do you define cos hyperbolic z? It is cos hyperbolic z, 2 times of cos hyperbolic z is ez plus e minus z, and 2 of sine hyperbolic z is ez minus e minus z. You use this and your conclusion will follow, and same goes for the last question. Okay, so the correct option is 1 3, I think, 1 3, yeah. Yeah, this is also true, this is also true. Yeah, so this fourth is not sixth. Yeah. Now the last question. So the last question is, if omega is an open connected subset of C and f is a holomorphic function on omega, and suppose we have f equal to u plus iota v, where u is the real part and f is v is the imaginary part, then which of the following statements are true? So the Cauchy-Riemann equation. So what is Cauchy-Riemann equation, which we know as CR equation? They are ux equal to vy and uy equal to minus vx. So clearly this is not correct, right? The minus are misplaced. So the statement is false. Now, the function f bar is always holomorphic on omega. Now, this is not true. Where f bar is the conjugate of fz. So if you choose your fz to be z, then f bar will be z bar. And we know that this is not holomorphic on the complex plane. Why? Because Cauchy-Riemann equation does not hold. So for if you define your g f bar z to be z bar, which is x minus iota y. So u is x here and v is minus y. Now what is ux? It is 1. What is vy? It is minus 1. So they are not equal. So which means they do not satisfy Cauchy-Riemann equation. Hence they cannot be holomorphic, this function. Okay. Now let's read the 3 4th and okay, let's prove one thing first, that if f bar is holomorphic on omega, then f is constant. Then f is constant. Remember that we are starting with the assumption that let f be holomorphic on omega. Okay. So if f is u plus iota y, and since because f is holomorphic, so which means Cauchy-Riemann equation holds, ux is vy, uy is minus vx, right? Now what is f bar? F bar is u minus iota v. So this will imply, if this is also holomorphic, if this is also holomorphic, then ux is minus vy, right? And minus of vy, sorry, uy, it should be uy, and uy should be minus of, okay, to do one thing, it is confusing, u minus iota v, write it as capital U plus capital iota v, capital iota v, where capital U is small u and v is capital V is minus v. So Cauchy-Riemann for f bar, because f is holomorphic and f bar is holomorphic, we have assumed 1 and 2. So capital of ux by Cauchy-Riemann equation, it will be vy, and capital of uy, it should be the capital V of x. But remember, capital U is small, same as small u, so it will be small ux, and v differs by a minus sign, so capital V of y will be minus v of y, and similarly capital U of y will be same as u of y, and capital V partial derivative capital V with respect to x will be minus of vx. So we have four equations. We have four equations. 1, 2, 3, 4. Now if you use 1 and 3, it implies ux equal to 0, right? 1 and 3, this ux equal to vy equal to 0, and 2 and 4, this implies uy equal to 0 equal to vx on omega. Now what is f prime z? How do you define f prime z? It is ux plus iota vx, right? So it is 0 on whole of omega, and because omega is a connected set, it is a domain. If derivative is 0 on an open connected set, the f has to be constant, right? F is constant. So what we have proved so far, if f bar is holomorphic on omega, then f is constant, right? So fifth is true. Now let's go for the third option. If f bar is holomorphic in omega, then ux equal to minus vy, uy equal to vx. They all are 0. We have proved, right? They all are 0. So third is correct. And fourth says ux and uy are identically 0. This is also correct. So third, fourth, fifth, all of them are correct. So the assignment is complete. If you have any doubt, please ask. Otherwise, I will finish the meet. Do you have any doubt? Okay, then if you have no doubt, you may leave. How half is fixed in fifth question? Okay, let me just go back. Yeah. So we defined this isometry. So you put the value half. So by definition, it is minus half plus 1. So it is half. So what we are getting, phi of half is half. So phi is fixing half. Okay. Is this clear, Pooja? Okay. Any other doubt? No. Okay. Okay, then if you have no doubt, then we'll meet in the next session. I'll upload this video on the YouTube. Okay. Okay. You may leave the session.
Thank you.
Welcome, welcome, Pavitra. Okay, welcome, Manik. Okay then. Bye guys.